Okay. Not sure if my clicker works. Clicker actually works. Welcome to this ultimate the battle between good and evil, between darkness and light, between streams and batch, and in general. I'm super excited that you're all here because it's the last session of the day. Energy should be high because after that we're gonna be partying, right? Yay! We're gonna be party, right? Okay. So as you can see, I usually expose high energy. So, stop me if you have any questions. If you hear something that you didn't like or you disagree, I'm totally cool with this. So, and today we're going to be talking about the two cool things that very close to my heart and very close to things what I do for the last, 5-7 years is stream processing, dealing with all things real time, Apache Kafka, all sorts of stuff. My name is Viktor Gamov. I work as a principal developer advocate at a company called Confluent. I'm also Java champion, and I know a few things about Kafka, and I also went and wrote the book about this. So if you want to pick up something interesting to read, Apache Kafka in Action, no, Kafka in Action, because there's a new book coming called Apache Kafka in Action. So mine is a blue title. You can reach out to me everywhere where you can find me. I'm everywhere on the internet, Twitter, Blue Sky, Instagram, LinkedIn, GitHub, whatever. And without this, we're going to jump right into the presentation. We're going to be talking about stream processing. And before, I can ask how many of you know what is it, how many of you don't know, anyone using Kafka these days in production, playing around, anyone? No one. Perfect. Even if you will tell me that you're using, it still won't change much. I don't know why some other speakers are asking people to raise their hands, because it didn't change the presentation flow, right? I'm going to start with explaining what's stream processing. I will give you background about Kafka, about what you need to know in Kafka world in order to understand the rest of the talk, because all the things would be focused around streams of data. It's not streaming video, it's not streaming audio, it's the streams of data. Data will come into stream fashion, meaning that they will never end. And Kafka will be our source, which is de facto standard. Even some competing solutions, they implement Kafka protocol in order to support developers who already know Kafka. So this is very important stuff, and especially if you never use Kafka in 2025, that's going to be year for Kafka in your life. We're going to start strong, and after that, you'll find a better job. If you can find a better salary, we're learning this technology. So I will be happy to be the person to introduce you to this. All right? So stream processing, simple. Stream processing is the set of tools that designed to process events as they arrive. We're not going to be sitting there and waiting until all these events will arrive, or all this data will be there, or all the files will be uploaded. Whenever data is ready and we can make some decision based on this, we're going to be using this. And these decisions can be two types of these decisions. One decision that you need to do small transformation or small filtering. You don't need to have a memory of what happened before. It is called stateless stream processing. Whenever you need to have some sort of memory of things that happened before, it's the stateful stream processing. And we're going to be focusing on the things, how to do aggregation, how to manage the state of your application, state of your processing. All those things I will be covering from perspective of two most popular frameworks that exist today. Now, what is Apache Kafka? Apache Kafka is distributed event streaming platform based on the data structure that's called log. Apache Kafka is distributed log. Log is just a file when you're writing data into end of this file, and after that you're reading sequentially. That's it. Another few cool data structures that you can pick up. It's a hash map and B-tree probably, because this is something that you need to know to design the database. But majority of database uses the data structure to capture all these events. Kafka is a distributed system, meaning that everything not going to fit in one particular node. Everything going to be distributed across multiple different nodes. And the way how Kafka does it, by sharding or partitioning this data through cool. All right. does this through partitioning this data structure. So this data structure will be available on each and every node. Sometimes you can replicate this in case of you need to preserve this data in case of failures. But essentially, immutable log, all the messages that comes into this log will contain some metadata, key, value, timestamp, and everything would be stored inside this log. You can ask, Victor, but is it like if you have a key value, can you do key value search on this one? Short answer is no. Kafka is designed to be a system where you read sequentially. And this is the core concept of dealing with some of the things that's stored inside the Kafka. Topics, you can have a multiple topics. Very similar analogy with the topics is that if you ever work with a messaging system, you know what the topic is. If you ever work with databases, it's a abstraction that stores your data in databases. Tables in databases, topics in Kafka. Each topic might contain multiple partitions, and this is way how the Kafka scales a read of this data. If you want to increase throughput of particular topic, meaning that you can increase how many users or how many applications will be consuming from this, and this is very important aspect. We're going to spend a little bit more time here. You will increasing number of partitions. Now, two basic concepts or two basic APIs that every developer would be using dealing with Kafka, regardless of the language, because right now, a language situation is kind of stable. There is a Java implementation, which is kind of sort of reference implementation, and there's a C++ implementation called librd Kafka, which used as a foundation for clients on Golang, Ruby, JavaScript, .NET, and all possible languages. And they follow same API. You need to know what's the producer, what's the consumer. Kafka producers send the data into Kafka, so the data will be captured in this immutable distributed transactional log. Client-side routing based on key. Since we have a key value, we can specify key. In this case, routing will be determined based on this key, and particular partition will be chosen to the storage for all the messages for the same key. They will not be overwritten because this is transactional log and the messages are immutable. So you can have multiple messages with the same key. They will land in the same partition and they will be preserved in particular order. Meaning that you can implement use cases like credit card transactions. For the same credit card number, all transactions will land in the same partition in the same order how this transaction happened. This is very important to perform ordered processing of those transactions. There's a concept of idempotent producer that defines and creates a foundation for what we call exactly one processing. So there would be no network interruptions, or producer will be handling these issues and not going to be sent same message with the same ID a few times. So there would be no duplications if you're using idempotent producer. Messages inside, in order to optimize it and speed up some of the processing and some of the deliveries, can be compressed and can be batched in these like smaller batches that will be packed in one TCP packet. The data producing, we're always producing at the end. We're also capturing position of this particular message. It's called offset. Thank you. And when we're producing without key, we're going to be randomly on the round robin based on null key when we be placing this on the random partitions. Because the applied function, consistent hashing function, that will make sure that all the messages with the same key will land the same partition. Now, reading. What do we see here? We see mommy bird. We see it. There's baby birds. Ooh, yeah, mommy bird, baby birds, and they sitting inside a nest. This is what you see. But when I look on this picture, this is what I see. This is what I see. This is what I see. Consumer group coordinator is the part of the server-side Kafka or part of the broker that will be responsible for distributing some of the load for consumers, aka baby birds. Mommy bird is the consumer group coordinator. And our nest will be defining consumer group. Consumer group is your application. Essentially, instance of your application will be defining this nest. Each individual, the members of this consumer group, is individual baby birds, will be responsible for handling some data. We have a Kafka topic. Mommy Bird brought us new topic with five very tasty wormies. That's our 5 partitions. If we have 5 baby birds, everyone will get evenly distributed, and every consumer in this group will be consume only one worm. What's going to happen if it's going to be like another consumer, another baby bird hatched? What do you think? It will starve. It's not going to die. It will starve, but maybe not going to die. It will starve. And the same way, if you're going to start more consumers that you have partitions in your topic, one of the consumers will be idling. It's also very important for understanding scalability that we have available in Kafka Streams. What's going to happen if one of these baby birds will fall out of nest? There's no answer, like at least like wild guess? There's no wrong answers. So what's going to happen if there's like a very tasty food and someone decides not to eat this tasty food? What's going to happen? Someone will take over, right? So I will take 2 plates and I will eat it myself because it's so good. Same thing that these baby birds will do. One of these baby birds will take care of 2 partitions, and they will start consuming from the 2 partitions. Same thing gonna happen with consumer group. If you have a less consumer groups than number of partitions, there would be distributed evenly. Some of the consumers will consume more than others, okay? That's very important to understand. This is how we're gonna be scaling some of our applications. Now, offset is also important point in understanding Kafka. Offset is something like a bookmark. Imagine Kafka is one book that's going to be shared across multiple users and multiple readers. And the same book, they consist same the data, and the different readers read this book with different speed. Same thing, different application that consume data from Kafka can consume it with the different speed. Some of them, based on their use case, they will be doing stateless stream processing. They will be just filtering results. Same thing as how I'm reading books. I'm just trying to find the pictures there, and that's why I'm reading super fast. Especially like big books without pictures. I can finish them super quickly. Some of the people can be much smarter. They might be, or maybe not smarter, they might be trying to read a book on some language that they don't know, so that's why they need to use another dictionary to find definition of these words. So essentially, we're joining 2 streams from the book and from outside source in order to get enriched result. And the third application can do something even crazier, maybe counting all the numbers or counting all the words inside this book. So source of the data will stay the same. Every time you are ready to reprocess it or reread data from Kafka Atomic, you still will be able to do just simply throw away this bookmark and reset your offsets, and you will be able to read the data from the very beginning. So this is how we're reading. Things that you already learned from the birds example. Okay, so we have one bird, we have 4 worms, and this baby bird will consume everything. If we want to scale, we introduce another nest. It's going to be another consumer group. And the way how this baby bird will be consumed, you see, this is where abstraction is kind of like breaking down, but it's still good abstraction. And you can scale those applications independently. Some of the applications, for example, if you do stateless stream processing, you don't have to be like super worried about storage of these individual nodes or processing speed because you just simple filtering or do simple transformation. For some use cases, you might want to scale this differently and so far and so on. Same thing with the one of the consumers inside the consumer group, in case of failure, will take over consumption from particular node. Kafka is a famous author of some very dark literature, follows similar principle. It's just like you write once and many people will read. Kafka is designed to handle both high throughput producing applications. There's ways how you can optimize it and write like super fast into Kafka. And also, most importantly, consumption. And many different consumers can read data from the same source, and they might get different results based on the use case that they're trying to do. And in order to get those results, you can obviously use producer and consumer and implement this stuff yourself. No one prevents you from doing this. But you know, some people doing hobbies to, I don't know, go fishing. Some people like to reinvent the wheel. So that's why writing stateful stream processing system is hard. And you will understand why it's hard in a few more slides, because I have like a very scary diagram that explains nothing. But don't despair, I'll explain you everything. Now, why we have these two funny animals? We do have one contender is Apache Flink. Anyone heard about Apache Flink, or maybe used Apache Flink, or few people? And the mascot for Apache Flink is squirrel. I don't know why. Something to do probably with Germans, because the majority committers and founders of Flink came from Berlin. They were the University of Berlin. They were inventing the Flink there. Another, it looks like a beaver, but actually it's otter. And otter is a mascot of the Kafka Streams. So what I like to say about things like Kafka Streams is great in-store brand. It's actually something that comes with the, like a battery included with the system. When you get Kafka, you get the Kafka streams to process your data. You don't have to, you can opt out for using producer consumer and go in the Kafka streams route where you start like a producer, perform your application. So, and we're gonna be comparing two different approaches. They doing same thing. They do stream processing. They do stateful stream processing, but they do this very drastically, in a very drastic ways. When I said the scary diagram in a few more slides, scary diagram in 3, 2, 1. So my slides are not advancing for some reasons. Sorry for breaking this. Yeah, so very scary diagram. Okay, step back. So this is the typical diagram that will be representing Kafka Streams application. There's something that you will be writing as a developer. So we have developers, right? So we do have developers writing code. Any Scala developers here? All right, okay, Scala developer. I need to get the why Scala developer got lost in the forest. Because they keep following traits and forgot how to get back to object. So I do have a few more Scala jokes if you want, but maybe not today. You know why Scala developer went broke?
Viktor, very important.
Yes, sir.
About why squirrel.
Please. Founders.
Yes. A colorful squirrel was chosen because squirrels are fast.
Squirrels are fast. Otters are cute and nice. You can cuddle. So, oh, different thing. Okay. So now we know the squirrels are fast and they nuts. This is how you're going to be feeling when you're writing the, say, data stream APIs using Flink. Anyway, I digress. So Kafka at the bottom, this is the central thing. And this is very important to point out in this particular case, because there are some other implementations, but Kafka Streams only works with Kafka. It doesn't work with anything else. Technically, it can work with the alternative implementation of Kafka, like Red Panda, WarpStream, even Pulsar. Anyone Pulsar? Yeah, I mean, like, you know, who cares about Pulsar? I don't understand. Yeah, they can work with Kafka because Kafka Streams has very intimate relationship with Kafka. So let me explain. So first of all, we can connect this source topic information into our Kafka Streams application. And after that, the results of our processing will go into Kafka Streams. So that's the Kafka cluster. Second thing is that it is a library, meaning that as application developer, it's a JVM library. You can embed this in any JVM application, Java, Kotlin preferably. There's even Scala API, but I think we're going to deprecate this soon. because no one is using this. So yeah, inside this application, you're writing two types of APIs. One API that usually in documentation referred as DSL, but I feel like it's a slightly oversimplification or maybe the unnecessarily complication of the name. Essentially, if you're a Java developer and you were born after Java 8, you very familiar with Java Streams API and how streams change the way how you perceive data processing inside your Java applications, Java util stream. So essentially, the inspiration for this like DSL-like API is a Java util stream. And another one is more low level, when you actually, by hand, building what we call direct acyclic graph. That's essentially, that will be representing your processing. Have a beginning, which is going to be sourced from Kafka, and end is going to be also dumped somewhere in the Kafka. And in between, there could be stateful operators or stateless operators. If we need to deal with the stateful operators, Kafka Streams provides with the libraries. Where is it? Where's my? Why are we not doing this? Yeah, so the, what's going on? Why is this not working? The Kafka Streams provides capabilities to store state locally, meaning that if we're running some aggregation, this aggregation, you don't need to store it in some hash map. You don't have to store it somewhere else. It provides you API to store this. You just say that materialize as, and it will create an instance of this embedded database called RocksDB. And after that, in case of this instance will go down for some reasons, Kafka Streams provide capabilities to replicate this state back to Kafka as a backup. So when your application will be killed, you need to restart this as application on another node somewhere. Application will restore the state from Kafka and continue processing where they left off. This is very cool capability, and it gives a lot of worries removes from developers' mind. However, with great power comes great responsibilities as always. This state can go big very fast, and in default configuration, you also need to understand that, like you might experience situation when you have a big state, a few gigabytes. There's no magic. There's no free lunch. It will take some time to recover this back from the Kafka topic, in case your local store was corrupted for some reasons. So that's the Kafka Streams. Any questions so far while we on the kind of like a basis of this infrastructure? So when there's a quiet in the room, there's always two options. Everything is clear or nothing is clear. And for me, it's difficult to figure out without you speaking up. I assume everything is clear because I'm doing the awesome job. But if you want to prove me wrong, tell me, I'll stop and explain. If you thought that was scary, wait a second. We're going to take a look now how Flink looks like. Remember, when I start talking about Kafka Streams, I mentioned one important point. Kafka Streams is a library, meaning that it gives you flexibility on how you're going to be using this. If you want to use just Kafka Streams inside your Tomcat application server, you can do this. If you want to deploy this as a Docker container, as a single jar, you can do this. If you want to run this as a part of, I don't know, some sort of like a desktop application, you still can do this. Maybe not advisable, but hey, I'm not the one who tell you what to do. Now, with the Apache Flink, it's freaking combined, because Apache Flink was designed to be general purpose stream processing framework. So in the contrast from Kafka Streams, Apache Flink doesn't have this kind of like intimate shenanigans with Kafka. It's just one of the things that Flink can do. And in the world of Flink, there's some different connectors that allow you to consume data from there. It's like a source connectors. Or there's a sync connectors that allow you to dump data after you perform certain computation. So that's why you can find those sources over here. Kafka topic can be here, file system can be here, and as a result, it can be some custom sync that will be maybe dumping to some REST endpoint. It's also possible. Small remark, in the world of Kafka, it also can be achievable with Kafka Streams and plus Kafka Connect. Anyone heard about Kafka Connect? It's another framework that also in store brand that also comes together with Kafka, and developers for different vendors of databases, messaging systems, different APIs, they usually provide some sort of implementation of this Kafka connector that implements certain APIs. So technically, you still can do things with the external sources. However, they need to land in Kafka first. It's not the case with the Flink. Second thing, that it's not application. It's something that you run in cluster. This cluster will consist of a job manager and bunch of task managers. So when as a Java developer, you're writing your application, you compile this into one fat jar. And after that, you submit this jar as a job into job manager. Job manager will recompile this jar file, will extract this data stream API topology, turn it into tasks, and send every task to task manager. And based on the resources available in the form of task slots, these jobs will be executed there based on the logic of your execution. And the scalability here is not tied to any sources. Usually, developers, they doing some sort of usually it handled on the input stream, on the connector side of things. For example, Kafka streams rely on Kafka, and it also relies on this key value model that Kafka messages have. Flink doesn't have these capabilities. It just relies on stream of something. And as a developer, you need to turn the stream of something into the something that will be represented stream of key values in case of Kafka. So that's additional step that you need to do. So that's a Flink in a nutshell. You are running this in different environments. You can define multiple different clusters. They have a very nice UI that you can see how the jobs are distributed, how this particular job will be compiled, what kind of resources will be used. So all this information is available, but this is something that you need to take in consideration if you start thinking about building stuff with Flink. I already talked a little bit about job manager, task manager. Now, next thing is that one important state management. The thing that I already mentioned, and I'm trying to stress this enough, that it's a stateful stream processing that will require the accumulation of some data somewhere. And simple, again, use case aggregation, any type of running averages, you can do any computations. Windowing operation, we're going to talk in a few moments. We're going to be also talk about how to, since it's a stream, there's no end and there's only beginning, there's no end. How we're going to deal with the situation where we need to get the result or get some sort of result, and this is going to be Windows going to be answer. Now, state management in Kafka streams. Your application instance will have ability to store this local state store in the form of key value API that will be backed by underlying implementation. Default implementation is RocksDB, but you can implement any type of state store. We've seen the implementation of Redis would be used as a state store to store this information in Kafka streams. Now, and the Kafka streams does, as I already mentioned, does some cool magic in between. So your application, the stream processing application that runs the Kafka streams, will be updating that state store. But underlying technology also will be listening changes that happened on this state store and turn this, the database would be represented local state store into something that would be stored in the replication topic inside the Kafka. So that's the that's basically changelog and the backup that will be stored inside Kafka topic. So in Apache Flink, it handles very similarly, but this state store will be bound to the task manager. And in this particular case, this is something that also done in a very clever fashion. They also use RocksDB as a kind of like implementation of this state store. And the Apache Flink, in order to persist or recover some of the nodes in case of failures, they have this concept of checkpoints. In the world of Kafka, I like to think about those checkpoints as kind of like our offset. We got the message from Kafka, we did some processing, and we write the result back, and we advance offset. So this everything can be done in what we call exactly one fashion. So it is going to be one operation, and if it's something fails somewhere in the processing, this message will now never be committed, and also offset will not be advanced. So the application will retry. So in the Flink, they have a similar ideas that sometimes, and this is something that you configure, some jobs needs to dump current state of the application, and essentially it's kind of like it freezes everything, the objects, data stream API, graph, everything will be kind of like a binary stored on disk. So in case of restart, they will quickly recover from this particular checkpoint. If there would be failures between checkpoints, obviously it will recover from checkpoint, and you're still not going to be processing from the very beginning. You will be processing from this kind of delta between two checkpoints. Now, the scalability aspect of these two things. We already touched this a little bit when I was talking about the overall application architecture, but in general, remember birdies in our consumer groups? That's the only way how you will scale, kind of, in a nutshell, scaling Kafka Streams application. Inside every instance of Kafka Streams application, there is a special consumer that will be constantly reading data. There will be a thread that will be executing all these operations. And in the Kafka Streams world, this task will be executed per partition. Say you have 8 partitions, and it will create 8 tasks to perform this particular computation. Why it's done this way? Kafka Streams is share nothing architecture, meaning that each node of Kafka Streams, they're not talking to each other. They don't know anything about their existence. They know about only their small world. Because Mommy Bird, consumer group coordinator, Kafka broker, this is where this metadata will be exchanged. So only this information will get kind of like a need-to-know basis. So they're not talking to each other. And in order to perform this, the multi-threaded or like parallel, highly parallel, the processing, each individual partition will be handled only by one particular task. So there would be no interference from other tasks that will be handling partitions. If some of the data needs to be collocated, Kafka Streams can do reshuffle and create additional special topics where those data will be collocated inside one partition. So there still will not be any kind of like a conflicts. You don't need to use any locks and stuff like that. But it will create extra storage on Kafka in order to create this repartition, reshuffle situation. There's also capabilities to this state store can be in what we called standby mode. Remember situation when I tell you when the state can be so big that recovery will take some time. Well, you can actually use this capability of starving consumer that will not going to be consuming and processing data. It still will be running. But what it will do, it will be constantly updating local state from Kafka. So in case of failure, this one will take over and become the replacement for failed friend, and state store recovery will not take time because there would be only delta. Now, scalability of Flink is simple on paper, but you need to do more job yourself in order to scale this because it will involve scaling, starting new task manager instances or relying on something that's called the Flink operator. That will, if you're running this in Kubernetes, this thing that will be responsible for standing more nodes. But essentially, task manager, you can scale a number of times task slots where you will be running particular code. And this can be configured. Defaults might not work in some cases, so that's why if you see that you need to have a better throughput, this is something that you're going to be touching. Now, window operations. Remember I mentioned that it's unbound. Stream is just like flowing in. And sometimes you need to get a result, especially if it's a stateful stream processing. And the concept of windows deserve its own talk. And it would be really, really, really unhumane if I'm going to start talking about the windows without giving you all this background first. So probably next time. the windowing, it's a very important concept to define these small windows, like bounded windows in this unbounded stream of data. And the way how it's done with Kafka Streams, say, for example, you want to do stream-to-stream join. You cannot do this because you don't know, what kind of result would be. So you need to define stream-to-stream join, like 2 topics, you can join them, on certain window, because this window will generate this special type of state store that will have time aspect also bound to this. So each individual time window will have a persistence. There is ability to handle late events. If some events arrive after Windows close, there's a concept of, I forgot the name of this concept, but essentially there's a small window where some late events can arrive, they still will be reprocessed, and they will spin up right result. Because there's some situation when late events can happen. The Windows Store allow you to perform like these type of operations. In Flink, it's done drastically different. So they have this concept of the watermark that will be defining the flow of time inside the Flink stream. So remember, Flink by itself, like everything inside the Flink would be kind of sort of flow same way how it flows in Kafka, but it is performed in JVM memory, not like on the file system like Kafka does. So special objects will be injected into this like a data stream pipeline in Flink. Then on the other side, operators that would interpret these different windows, interpret like how they need to emit result from this particular window, they will be capturing this watermark, and this watermark will be signifies like, okay, so all the events that needs to belong to this window, they're already gone, they're already here. So they between those watermarks. You still there's opportunity to handle late events, but the watermarks is the way how this window will be defined. So Windows State Store is essentially going to be a table with extra dimension for time in Kafka Streams, and in Flink, a special type of objects that would be inserted into stream. Now, exactly once, very sexy topic, because when this was announced, I don't know, 5-6 years ago, that Confluent, the company that I'm working for, and they are major contributor to Apache Kafka, and we are also founded by people who started Apache Kafka, and when there was a blog post that, wow, they achieved exactly once. It's impossible! How it's possible? It's because it's impossible. So here's the thing, there's details about everything. And the way how the people perceive exactly once, not how exactly once implemented in Kafka. So people think exactly once is that someone will produce, some will process, and some will consume in one shot. This is not how it's done in Kafka. In Kafka, exactly once actually happens vice versa. You read data from Kafka, you process this, and commit it back. And this loop, this one particular execution on one particular instance of Kafka Streams topology, that's exactly once. If somewhere in between, like you do your flat map, you do your grouping, and something happened, whole process will roll back from the beginning, and maybe some other node will take over and will continue from this point. So the process of consuming, processing, and producing back, and also advancing our offsets, this is what happens in exactly once. Since Kafka Streams relies on Kafka exactly once, since it's a like so good relationship between those two, there's not much needs to be done. Actually, there's a lot. A lot internally, but as a developer, you just need to go do configuration, exactly once enabled, that's it, you're golden. So you're getting this immediately. And to be honest, I think one of the reasons, the main reason why exactly once was introduced, including the transactional producer, including the producing into multiple partitions in the same transaction atomically. I think it was done in order to perform exactly once processing with Kafka Streams. That was like sole purpose of this implementation. And this is how it's done. Now in Flink there's a case-by-case basis, because this exactly once processing needs to be implemented in in the systems that sources support exactly once, because Flink is a general purpose system. There's some knowledge based on the connectors of other systems, but in general, the engine that processes the data, it doesn't really care whether data come from Kafka, Pulsar, Kinesis, or from database. So it needs to be something that handles kind of this, and the implementation of exactly once would be like a case-by-case basis. And I think that right now there's even on the Kafka side of things support. Flink supports exactly once. There's some improvements that come into Flink 2.0 and Kafka 4.0, but it's much harder how it's implemented in Flink than how it's implemented in the Kafka streams. All right, cool story, bro. But what shall we use, right? You get this kind of like, okay, what's he talking about? So, as a developer, if you're writing microservices, if you're writing any type of system that will need to make a decision based on the Kafka, you need to update your state of account based on your new transaction. You have a microservice that will be running total for your bank account. And the Kafka will will represent your ledger. And you need to have a REST API that you call, and here's my account number, give me a total. That's a good example to implement this with Kafka Streams. Super easy, all these low-level. As a matter of fact, I think in Kafka Streams in action, I have this example of bank transaction processing with the Kafka Streams. And it's super flexible for deploy because it's a jar. You include the jar in your application. There's a bunch of dependencies like Kafka clients. There's a support of schemas if you, in this type of JS. And again, it deserves its own talk. It comes with very cool framework called the test utils, a super exciting name, but it allows you to perform testing of your topology without even starting Kafka, without even starting application. Topology test driver is a super nice framework that I like to use. Built-in exactly one semantic. I would say it can be downside for some cases, so it's only Kafka-centric, but also it's better included in your purchase. Now, Apache Flink, it's a monster of the things. It can do pretty much everything with your data. Uber uses Flink to do all sorts of things with the car matching. Netflix uses heavily Flink in their infrastructure. There's a bunch of talks on Kafka Summit London, currently Austin, the cool talks from the different vendors. Massive stateful operations because you have capabilities to deal with the state in a more efficient way. There are checkpoints. You don't have to recover whole store how we need to do with Kafka Streams. We do have the cool concepts with dealing with watermarks, and it would be unified API between different sources, including a batch and stream. In the Flink, the batch processing is just a corner case of streaming. It's just a bounded stream, which is also cool. You can use Flink to do batch processing. Very complex window operation and late event handling. I didn't even talk about this, but Flink has Flink SQL. Forget about me trashing Scala in Java. You can write the same thing in just one tiny, not tiny, but in one SQL statement. It doesn't mean Flink makes the streaming database or something like that. It's just a language that used to turn something familiar that you're familiar into the jobs that will be executed by Flink. Also, there's a bindings that allows to interact with Flink through Python called PyFlink. All right, so with this, my name is Viktor Gamov. As always, have a nice day. Do I have, how much time do I have already off? A couple minutes. I actually started working on some of the examples. I want to quickly show you a couple things. So if I will talk with the flight delay processor, so, sorry, it's a Flink. Where's my Kafka Streams? This one. So the way how my processor would look like in my application, that we have this, oh, snap, it's a dark mode. All right, so let's do this. Yeah, that's better. All right, so the, we do have an input stream that comes from Kafka topic. This is what we have. Now, we do have a duration for which we're capturing. It's a kind of processor that captures delayed flights, and I have if it's going to be delayed for 15 minutes, I need to be considered delayed, and there would be different stream that will include only delayed flights, so I can reprocess this for an analytical purpose. So I'll get the report, and after that, I'll start kind of checking who will get bonus or who will not get bonus in terms of, because obviously pilots are responsible for delay. So now, in this particular case, this is a simple use case that I'm using JSON. With more complex, I can enforce schema for my objects because in Kafka they store in bytes, but as an application developer, I will care about this. So there's operations that I was talking about. Those operations are stateless. Peek is something that allows me to kind of look inside the stream what is going on there. So for this particular reason, I'm just putting this into log context. There is a functions to perform aggregation when windowed by our particular time window that we, in this case, is going to do aggregation of certain flights by route, so we can get accumulated results. And there's a bunch of things I can do with the materialization. So I store this into my, what's the store name? I don't see it. Yes, routes, states, store that allow me to query this. With Flink, that's much more complex. So first of all, we're defining this Kafka source as our input stream in this particular case. And after that, once we define this, we also defining the strategy for watermarks in order to establish same windowing capabilities. The next thing is that telling that we're creating new data stream. In Kafka Streams, we're talking with the topology. Here we're talking about with data stream. And this is the point where we need to rekey this stream because Flink doesn't know anything about the keys. We need to tell this, and in our use case, key is important. Windowing through same approach, very similar approach. It looks similar on API implementation details, obviously different. And now we do have a sink that takes this data that we just processed in our time window to pick up the delayed flights, and we dump this into other things. And as you can see here, I can dump this in 3 different streams. If you have Kafka streams, I can't do this. There's a branch operator, there's split operator. You also will be able to do this type of jazz. So that's kind of in a nutshell. If you ever will be in the United States, there's a great conference. Let me put it this way. If you want to have a purpose to go to the United States, there's going to be a very cool conference in Atlanta in March called DevNexus, probably one of the best conferences in the US. I will be doing whole day training about Flink. Hopefully, I will see many of you there because it's the beast of the system. And one of the things what I also wanted to quickly show you. Where's my? There should be something like. If I go to LL Flink, and where's my build? I wanted to show you that as a result with Flink, you have a zip file with all these classes. It's a fat jar that you upload to your Flink cluster, as a result, you will be running this in cluster. Kafka Streams has a testing that is under. You can stop me because I can talk about the shit all day, kind of thing. If you say Viktor, enough. There's a lot of cool things that we can talk about. Hopefully, some of this was helpful for you. Hopefully, that something was useful. If you ever will be in a situation that it was cool, but where you can find the results, developer.confluent.io. It's the best portal where you can learn everything about Kafka, everything about Kafka Connect, everything about Kafka Streams, Flink, and much more. Thank you so much. We do have some time for enhanced interrogation, so if you have any tricky questions, I'm happy to answer.
Can you use Kafka's CQRS architecture?
Yes, absolutely. Can we use Kafka Streams for CQRS architecture? There's a bunch of examples that use Kafka Streams for this use case. You can implement event-driven microservices CQRS using Kafka Streams.
Could you suggest any strategy to manage the priority?
Can I suggest any strategy to manage priority? I don't think the system like Kafka doesn't have anything built in this, so your application logic needs to handle. Flink has a library for complex event processing. You can take a look, maybe some of the primitives available on the Flink side of things in order to perform, the priority queues and all these kind of things that you need to implement. But it is, I would say, some of the things can be implemented on the Kafka streams. Say, for example, you want to have, I don't know, for the minute, you want to wait until the 5 certain messages will arrive in one particular window, and inside this window, inside this code, you can reshuffle and change the order to send this back. So there's examples of deduplication, and maybe you can adopt some of those examples for priority, because there's multiple different things that going on, like what kind of level of priority, how you want to specify it, what does it mean priority for your application, like what's going to be like a result, what's a hassle with this priority. So there would be much more to discover. I highly recommend either come to our Slack community, and Confluent manage Kafka Slack community, where everyone's super nice and everyone's super cool, and probably someone can suggest you to priority use case implementation. That's a trick. I can do this all day. That's why I'm kind of creating this awkward silence. I can tolerate, but people who are not prepared, they usually start, okay, so like, am I leaving? But like, I cannot leave right now because there's maybe something is going on. Okay, let me try to ask the question. You may go. If you have any questions, you can find me. I still will be around here for quite some time. So again, thank you so much for coming, and it was great.